Okay, so we're still working with exponential growth and decay, but now what we're doing is we're working with things that have what's called a half-life. And the definition of a half-life is the amount of time it takes for the original amount of a substance to be down by 50% or to be down to half. Okay, I'm going to just type this instead of write it. The length of time it takes for the original amount of a substance to be down to half of that amount.
Like the coffee.
Like the coffee, exactly like caffeine. We're going to put that as one of our examples. What else do you know that has a half-life, Maya?
Medicine.
Medicine. Radioactive material. Let me see what else. Those are definitely the main ones. I'm gonna see if I can find some more examples.
As a joke, I was gonna say shaving wood.
Oh yeah, like cutting the wood down.
Yeah.
I don't know that it would exactly be half the amount, but maybe with.
Because like when you shave the wood, there's like wood chips all over the place.
Exactly. So just looking up to see if there's more. Uranium, that's radioactive material. Plutonium, that's a radioactive material. Isotopes. I think we got the main ones here. Yeah, it says medicines or drugs. We have that. Okay. I think we have the main ones here. That's good. So with these questions today, we're going to just be given a formula and then we just have to use them. Now the formulas sometimes look complicated, but it's just a matter of plugging in a number and then using your calculator. So Maya, we're just going to have to get really comfortable with our calculators and I'll help you with that today. This says the bacteria culture began with 7,500 bacteria. It can be modeled by this equation where T is the number of hours. This one is actually going to be exponential growth because it's doubling, it's multiplying by 2, and it doubles every 36 hours is what this question is saying, okay? So the bacteria starts at 7,500, it's going to double every 36 hours. So the first question is how many bacteria are present after 36 hours? So T is hours. So that's going to look like this, 7,000 times 2. Now, Maya, what is 36 divided by 36?
1.
1. So this is actually a simplified equation. You're just doubling 7,500. So what would that be?
When you have 1, it turns into 0. No, wait. When you have an exponent, I forgot what happened.
Oh, it just means it's a 2. It's just times 2.
Okay.
Yeah, I can
So
actually.
it's just like, it's just 7,500 times 2.
Yeah.
Is 15,000.
Very good. So you end up with doubling the number after 36 hours. Now what they're asking us to do is figure out how many there'd be after 72 hours. So we can simplify this, Maya, but I have 70. Oh, I didn't mean that 1 there. 1 second. Maya, what's 72 divided by 36?
2.
Okay. So I got to take 7,500 and times it by 2 to the power of 2. Or if you want to make that into a 4, you can. What do we have?
sorry, wait.
That's okay. I'm getting 30,000. Maya, are you getting the same?
Yeah,
Good. So you can see it doubled from here to here. It doubled because 72 just means you took 36 and doubled it again as far as the amount
Yeah.
of time that you have, right? So you can see that it just doubled one more time. And it would continue doing that every 36 hours because that's bacteria doubling. Now let's see what happens if it's something about exponential decay. Oh, here's an example, carbon dating. I forgot about that, but it is a radioactive material here. All living organisms contain a certain concentration, 1 part per trillion of carbon-14. Carbon-14 is a radioactive element. It's used to date ancient artifacts. Its half-life is about 5,730 years. So they do know the time it takes to break down, which is where this equation came from. So I'm not asking you to put it together, we just have to use it. How much carbon-14 would be in a piece of cloth after 5,730 years? Well, Maya, you're going to see here. What is 5,730 divided by 5,730?
1.
1. So what's 1/2 to the power of 1?
0.5.
Yeah, so it's going to be at half the amount. So if the initial amount had, let's say 10,000, the concentration was 10,000. After 5,730 years, it's going to be down to 5,000. So they can use that for carbon dating. So it'll be down by half. This one's saying, what would be the concentration of carbon-14 in animal bone after 10,000 years? So a half. Maya, can you do 10,000 divided by 5,730? So we can just reduce that.
1.745 and a bunch of other numbers.
1.745.
4, 5.
Maybe give me
0, 0.
okay, that's that we can leave it there. So now Maya, do 1/2 to that exponent and tell me how much carbon-14 would be there after 10,000 years.
Do I have to put the half in parentheses?
You're going to have to play around with your calculator to determine that. I don't have to, but I have a fraction button. So Maya, you might have to just play around with that. I'll put it in my calculator and let's compare. And then you can see if you need to or not.
Okay.
What'd you get, Maya?
I got 0.298.
Yeah, I'm going to round to 30, I think, because I have the same number as you. So it's about 30% remaining. So the formulas look complicated, Maya, but it's just a matter of like plug in the data given to you in the word problem. With your calculator, I would recommend simplifying your exponent and then doing the actual calculation.
Okay.
Do you have any questions on any of that?
No.
Okay, that's the whole lesson. It's still just a continuation of exponential growth and exponential decay.